let's jump right in. Welcome to the Explainer. Today, we're looking at something absolutely foundational. Seriously, every single embedded system around you, from that little blinking LED on a toy, to the advanced motor controller zipping a drone through the air, all the way to your whole smart home setup, it all depends on one tiny critical feature. It's the digital physical bridge. And getting a grip on this, it is literally your first step into the wider world of embedded systems.
Okay, let's dive into this. Have you ever actually stopped to wonder how a tiny piece of silicon knows when you physically press a button? Like you press it down, an electric signal rushes down a wire, but how does the digital brain inside that chip actually interpret that analog physical action? It's a bit of a mystery, right? Bridging that gap between the physical, messy world and the neat digital world, well, that is exactly the puzzle we're going to solve today.
The answer to our mystery? It's all about GPIO. That stands for General Purpose Input/Output. The best way to think about GPIO pins is to imagine them as programmable electrical doors. You've probably seen those little metal legs sticking out of a microcontroller, right? Well, unlike some pins that have one very specific hardwired job, GPIO pins are completely flexible. The software gets to call the shots. So today, you might tell a pin to send power to an LED. But tomorrow, you could rewrite your code and that exact same pin is suddenly reading a button press. Or maybe next week, it's driving a relay. It's that general purpose flexibility that makes them an absolute game changer.
To really wrap our heads around why we need GPIO, picture the CPU inside your microcontroller as being, well, trapped inside a glass box. It's this brilliant digital brain effortlessly crunching ones and zeros, but it is totally isolated from the analog world outside, the fans, the motors, the sensors. Somebody has to act as a translator between that trapped digital logic and the physical environment. And that is exactly what GPIO does. It serves as that crucial translator.
And because it's a translator, it has to work in both directions, right? That brings us to input and output modes. Think of it like this. When a GPIO pin is configured as an input, it's basically listening. It just waits. Nothing happens until it detects a change in voltage from the outside world, like when someone presses a button. The CPU hears that and reads the change. Output mode on the flip side is the exact opposite. Instead of listening, the GPIO pin is speaking. The CPU writes data into an output register, changing the voltage on the pin to actively drive a connected device, like turning on a light or a buzzer.
And this brilliantly illustrates how the physics turns into math. Electrically speaking, all this listening and speaking comes down to voltage thresholds. When we talk about a high state, which might be 3.3 volts in a modern system, the digital brain sees that and registers a logic 1. When the voltage drops to a low state, or 0 volts, the brain reads a logic 0. The GPIO's entire job is to flawlessly map those physical, real-world voltages into the binary ones and zeros your code actually understands. Everything, and I mean everything, in digital electronics eventually boils down to these two mapped thresholds.
Now, you might be tempted to think a GPIO pin is just a dumb piece of wire, just a simple connection from the inside of the chip to the outside. But no way. If we zoom all the way in to the microscopic level, these pins are actually packed with hidden, incredibly smart circuits. Inside every single pin, you've got protection diodes standing guard against dangerous voltage spikes. You have input buffers acting like filters to clean up messy, noisy electrical signals. There are output drivers beefy enough to supply the actual current needed to push power out. And finally, registers. Those are the memory locations where your software actually configures exactly how all these other components behave. It's like a bustling little city in there.
But, even with all that brilliant internal circuitry, it can't save you from a very common, very frustrating physical problem: the floating input. Imagine this. You set a pin to listen, an input, but you haven't actually wired it up to anything yet. The pin has no idea if it's supposed to be reading high or low. It is literally floating in electrical limbo. Because of random ambient electrical noise just floating around in the room, the voltage on that pin fluctuates wildly. If you hooked an LED up to that reading, it would just flicker like crazy, and your software would just see a chaotic, unpredictable mess of ones and zeros. Not good at all.
So how do we fix this chaos? Well, what's really interesting about this concept is how microcontrollers elegantly solve the floating problem using pull-up and pull-down resistors. And the best part, these are usually built right into that internal GPIO architecture we just looked at. A pull-up resistor does exactly what it sounds like. It gently pulls that floating, unconnected voltage up toward the high state. A pull-down resistor does the exact opposite, pulling it down toward low. They act exactly like anchors. They completely stabilize the signal, guaranteeing a rock-solid, predictable reading even before you've ever pressed a button.
All right, let's put the whole shebang together and trace the complete journey of a signal exactly like you'd see on a real-world breadboard. Step 1, Your finger physically presses a button. Step 2, the GPIO pin instantly detects that sudden voltage jump from low to high. Step 3, the CPU reads that input register, sees the change, and fires off your code. Step 4, your software tells a completely different GPIO pin to change its output register to high. And finally, step 5, current flows out of that pin and bam, your connected LED glows. The craziest part? This entire incredible multi-step journey happens in mere milliseconds. You literally can't blink fast enough.
Understanding this journey is absolutely crucial because it is completely universal. Seriously, it doesn't matter what hardware you're using. You could be coding for an 8-bit Arduino Uno, maybe a 32-bit Extensa on an ESP32, an ARM Cortex on an STM32, or a Raspberry Pi Pico. These boards have wildly different architectures, totally different pin counts, and they run on different voltages. But every single one of them relies on the exact same fundamental GPIO principle, reading inputs and generating outputs. Once you truly get GPIO, you can transition between any of these boards with total ease.
Of course, messing around with the physical world means you can physically break things. So let's rapid fire through some common beginner pitfalls to keep your hardware alive, okay? First up, never exceed the GPIO voltage limits. If you shove 5 volts into a 3.3 volt pin, you are absolutely going to let the magic smoke out. Don't do it. Second, never connect motors directly to a GPIO pin. They draw way too much current and will instantly cause an overcurrent failure. Always remember your current limiting resistors for LEDs. And as we just learned, do not ignore your pull-up or pull-down configurations if you want stable, reliable input readings.
So the crucial point is this. Mastering these seemingly basic rules, high and low, inputs and outputs, is the absolute foundation for everything else in embedded systems. Think about it. Whether it's smart home automation, smoothly adjusting your thermostat, heavy-duty industrial PLCs, managing a factory assembly line, or a drone's ESCs instantly tweaking motor speeds to keep it in the air, all of these massively complex systems are just quietly relying on GPIO to do its job, reading the physical world and reacting to it. Everything builds on these basics.
But this brings us to a really fascinating limitation, and I want to leave you with this final thought. We know GPIO is incredibly fast, right? But remember, an input relies on the CPU actively listening to or checking that specific pin. What happens if your CPU is trapped in some massive, heavy calculation and is simply too busy to check the pin? If a critical sensor triggers at that exact moment, how does the microcontroller drop everything and react instantly without missing a single beat? Well, that limitation takes us beyond basic GPIO straight into the incredibly powerful world of hardware interrupts, which is exactly what you should be exploring next. Thanks for joining me on this explainer, and keep building.